What happens when the universe, after billions of years of silence, suddenly whispers a sign of life? James Webb has just discovered a planet with a 99.7% chance of life. Not a hypothesis, but a chemical signal as clear as a breath. Do you believe it? Or do you still doubt? Share your thoughts in the comments. And now, let us face the greatest question of all. Have we truly found signs of life beyond Earth? For a long time, the universe has felt like a cathedral after the choir has left. Vast, beautiful, and quiet enough that your own thoughts become the loudest sound. We have listened with radios, stared with telescopes, and waited for a single hint that the darkness is not empty. Now a new kind of whisper has arrived. Not a voice on a frequency, not a glowing ship, but a faint signature in starlight that dares to suggest a living process far beyond our reach. And that is why this question cuts so deep, because it asks whether the universe just blinked at us, or whether we are still staring at our own reflection in the cosmic mirror. The story begins with a claim that sounds almost too clean to trust. 99.7% confidence. In everyday life that feels like certainty, like the floor beneath your feet. In astronomy it is rarer, because space is not a laboratory bench you can control. It is a storm of light, dust, instruments, models, and assumptions that must all line up before you can say anything with a straight face. So when you hear a number like that, your heart jumps forward, and your mind should step back at the same time. That tension is healthy. It is the heartbeat of honest science. Carl Sagan gave us a sentence that should always be written on the door of every discovery announcement. Extraordinary claims require extraordinary evidence. This is not a brake that ruins wonder. It is a guardrail that keeps wonder from driving off a cliff. At the same time, Sagan also offered the hopeful counterweight. Somewhere something incredible is waiting to be known. Between those two lines, caution and longing, the whole emotional sky of this topic glows. So what is actually being claimed here? A telescope like James Webb does not take a postcard photo of alien forests. It reads the chemistry of an atmosphere by analyzing light that has passed through it. Picture a small world crossing in front of its star. A thin ring of starlight filters through the planet air. Molecules in that air absorb specific wavelengths and leave a pattern of missing light that behaves like a fingerprint. When scientists decode that fingerprint, they infer what gases are present and in what proportions. It is subtle work, like trying to hear a single violin string inside a hurricane. Yet this is the kind of subtlety modern astronomy was built to chase. Now come the details that make the audience lean closer to the screen. The planet in this story is described as an ocean world, wrapped in a thick atmosphere with a stable, warm temperature that can allow liquid water. The spectrum is said to show water vapor, methane, and carbon dioxide. These are not proof of life by themselves, but they form the stage on which the next clue becomes dramatic. Then the video centers on a molecule that on Earth is strongly associated with biology: dimethyl sulfide. It is presented as a scent of life, a chemical breath that living ecosystems tend to exhale. When you hear that, the imagination fills in the rest. Warm seas under a red sun, drifting clouds like silk, a slow oceanic metabolism that never sleeps. But here is where the serious question must sharpen. Is dimethyl sulfide truly a smoking gun in an exoplanet atmosphere? Or could there be non-biological pathways we have not yet accounted for under alien conditions? The honest answer is that science treats every biosignature candidate as a suspect in a lineup, and it demands multiple independent reasons before it calls the case solved. A single molecule can be powerful, but it can also mislead if the environment is different enough that nature invents new chemistry that mimics biology. This is why confidence numbers must be understood in context. They may reflect how strongly the data favors a certain interpretation under the model used, but models can change as we learn more about exotic atmospheres and ocean worlds. To make this easier to feel in your bones, imagine a detective smelling smoke in a hallway. On Earth, smoke often means fire. But a fog machine can also produce a smoky smell in a theater. The detective might say, "I am 99% sure something is burning." And under normal conditions that might be fair. Yet if the building is a theater and the stage crew uses fog as a special effect, the meaning of smoke changes. Exoplanet science is like that detective work. Except the building is a world you cannot enter, and the stage rules might be different from ours. Still, it would be unfair to treat this as mere hype if the analysis is careful. The strongest argument in atmospheric biosignature claims is not usually one gas in isolation. It is a pattern of gases that sit in chemical tension. A persistent disequilibrium that is hard to maintain without a continuous source. On Earth, our atmosphere is a living system in that sense, constantly renewed by biology that pushes it away from simple equilibrium. If an exoplanet shows a similar sustained imbalance and alternative explanations are systematically tested and weakened, the case becomes more compelling. Here is a second example to anchor the idea. Think of a bathtub where you keep the water level steady even though the drain is open. If you see the level staying constant for hours, you infer that something must be refilling it continuously. You may not see the faucet directly, but the behavior of the system implies a source. In the same way, certain atmospheric mixtures imply an active process replenishing gases that would otherwise disappear or transform. Biology is one candidate for that process. Geology is another. Photochemistry is another. The job is to ask which candidate can keep the tub levels steady under the specific conditions of that planet. And here is a third example that is almost meditative if you let it be. Imagine walking into a room and feeling a rhythm in the air. A gentle pulse of warmth and coolness repeating in a stable pattern. You do not know yet what produces it, but you sense that the system is regulated. Life is regulation, not perfection. It is a constant balancing act that never rests. Like breathing, like tides, like the slow circulation of oceans. When we say a distant planet atmosphere behaves like it is being regulated, we are basically saying it feels like a room with a hidden rhythm. Now, let us widen the lens to the emotional meaning of the number itself. 99.7% confidence sounds like a door almost fully open, but not quite. That last fraction matters because history is full of moments where humanity declared victory too soon. Have we truly found signs of life beyond Earth? For a long time, the universe has felt like a cathedral after the choir has left. Vast, beautiful, and quiet enough that your own thoughts become the loudest sound. We have listened with radios, stared with telescopes, and waited for a single hint that the darkness is not empty. Now a new kind of whisper has arrived. Not a voice on a frequency, not a glowing ship, but a faint signature in starlight that dares to suggest a living process far beyond our reach. And that is why this question cuts so deep. Because it asks whether the universe just blinked at us, or whether we are still staring at our own reflection in the cosmic mirror. The story begins with a claim that sounds almost too clean to trust. 99.7% confidence. In everyday life, that feels like certainty, like the floor beneath your feet. In astronomy, it is rarer, because space is not a laboratory bench you can control. It is a storm of light, dust, instruments, models, and assumptions that must all line up before you can say anything with a straight face. So when you hear a number like that, your heart jumps forward, and your mind should step back at the same time. That tension is healthy. It is the heartbeat of honest science. Carl Sagan gave us a sentence that should always be written on the door of every discovery announcement. Extraordinary claims require extraordinary evidence. This is not a brake that ruins wonder. It is a guardrail that keeps wonder from driving off a cliff. At the same time, Sagan also offered the hopeful counterweight. Somewhere something incredible is waiting to be known. Between those two lines, caution and longing, the whole emotional sky of this topic glows. So what is actually being claimed here? A telescope like James Webb does not take a postcard photo of alien forests. It reads the chemistry of an atmosphere by analyzing light that has passed through it. Picture a small world crossing in front of its star. A thin ring of starlight filters through the planet air. Molecules in that air absorb specific wavelengths and leave a pattern of missing light that behaves like a fingerprint. When scientists decode that fingerprint, they infer what gases are present and in what proportions. It is subtle work, like trying to hear a single violin string inside a hurricane. Yet this is the kind of subtlety modern astronomy was built to chase. Now come the details that make the audience lean closer to the screen. The planet in this story is described as an ocean world, wrapped in a thick atmosphere, with a stable, warm temperature that can allow liquid water. The spectrum is said to show water vapor, methane, and carbon dioxide. These are not proof of life by themselves, but they form the stage on which the next clue becomes dramatic. Then the video centers on a molecule that on Earth is strongly associated with biology: dimethyl sulfide. It is presented as a scent of life, a chemical breath that living ecosystems tend to exhale. When you hear that, the imagination fills in the rest. Warm seas under a red sun, drifting clouds like silk, a slow oceanic metabolism that never sleeps. But here is where the serious question must sharpen. Is dimethyl sulfide truly a smoking gun in an exoplanet atmosphere? Or could there be non-biological pathways we have not yet accounted for under alien conditions? The honest answer is that science treats every biosignature candidate as a suspect in a lineup, and it demands multiple independent reasons before it calls the case solved. A single molecule can be powerful, but it can also mislead if the environment is different enough that nature invents new chemistry that mimics biology. This is why confidence numbers must be understood in context. They may reflect how strongly the data favors a certain interpretation under the model used. But models can change as we learn more about exotic atmospheres and ocean worlds. To make this easier to feel in your bones, imagine a detective smelling smoke in a hallway. On Earth, smoke often means fire. But a fog machine can also produce a smoky haze in a theater. The detective might say, "I am 99% sure something is burning." And under normal conditions that might be fair. Yet if the building is a theater and the stage crew uses fog as a special effect, the meaning of smoke changes. Exoplanet science is like that detective work. Except the building is a world you cannot enter, and the stage rules might be different from ours. Still, it would be unfair to treat this as mere hype if the analysis is careful. The strongest argument in atmospheric biosignature claims is not usually one gas in isolation. It is a pattern of gases that sit in chemical tension, a persistent disequilibrium that is hard to maintain without a continuous source. On Earth, our atmosphere is a living system in that sense, constantly renewed by biology that pushes it away from simple equilibrium. If an exoplanet shows a similar sustained imbalance, and alternative explanations are systematically tested and weakened, the case becomes more compelling. Here is a second example to anchor the idea. Think of a bathtub where you keep the water level steady even though the drain is open. If you see the level staying constant for hours, you infer that something must be refilling it continuously. You may not see the faucet directly, but the behavior of the system implies a source. In the same way, certain atmospheric mixtures imply an active process replenishing gases that would otherwise disappear or transform. Biology is one candidate for that process. Geology is another. Photochemistry is another. The job is to ask which candidate can keep the tub level steady under the specific conditions of that planet. And here is a third example that is almost meditative if you let it be. Imagine walking into a room and feeling a rhythm in the air. A gentle pulse of warmth and coolness repeating in a stable pattern. You do not know yet what produces it, but you sense that. The system is regulated. Life is regulation, not perfection. It is a constant balancing act that never rests. Like breathing, like tides, like the slow circulation of oceans. When we say a distant planet atmosphere behaves like it is being regulated, we are saying it feels like a room with a hidden heartbeat. Now let us widen the lens to the meaning of the number itself. 99.7% confidence sounds like a door almost fully open, but not quite. That last fraction matters because history is full of moments where humanity declared victory too soon. A signal can be contaminated. A model can be incomplete. A statistical threshold can be misunderstood by the public. This is not cynicism. It is humility. Humility is the posture of a mind that has been fooled before and chooses to learn rather than to harden. Stephen Hawking once warned that meeting advanced extraterrestrial life might not be a gentle experience for us. Whether one agrees or not. The deeper point is that even the possibility of life elsewhere rearranges our psychology. It changes what we fear, what we hope, and what we assume about our own importance. This is why this video feels larger than a single planet finding. It is a meditation on identity disguised as a science story. Now let me add my personal view in the most honest way I can. I do not think we should treat any single observation as a final declaration of life. I also do not think we should shrug and say it is nothing. The balanced stance is to treat it as a strong invitation to continue listening with better instruments and deeper analysis. In my mind, this is like seeing a distant lighthouse flash once through fog. You do not claim you have arrived at the shore, but you also do not deny the light existed. You mark the bearing. You adjust your sails. And you keep moving. The poetic beauty is that Webb does this without traveling anywhere. It turns light into a messenger and chemistry into a language. Each photon becomes a syllable that crossed space for more than a century before touching a gold mirror and becoming meaning inside a human mind. In that sense, the telescope is not just hardware. It is a new sense organ for our species. It allows us to smell an alien ocean from the comfort of a small blue world. If you want an image to hold during the rest of the video, hold this one. A planet wrapped in thick air, where heat is shared gently around the globe. Above it, a small red star glows like an ember that refuses to die. Time there is generous, slow, patient. Oceans could remain liquid for ages beyond imagination. And if life begins in such a place, it may have had not just millions but billions of years to learn how to persist. Now let us return to the hook and press on it harder. Why does this question grip us so strongly? Because it threatens to end cosmic solitude. Because it challenges the old story that Earth is a rare exception. Because it makes the night sky feel less like decoration and more like a neighborhood filled with hidden rooms. Neil deGrasse Tyson said, "The universe is in us." Take that line slowly. If the same atoms and laws that shaped us can shape life elsewhere, then finding biosignatures is not just finding strangers. It is finding relatives in the broadest sense. And yet the lesson is not just outward toward the stars. It is inward toward our own habits. The video hints at a quiet moral without preaching it. If life can be common in the galaxy but fragile on a single planet because of what an intelligent species does to itself, then the discovery becomes a mirror as much as a window. It suggests that the true test of intelligence is not whether it can detect life across light years, but whether it can preserve the life it already holds in its hands. So what should the viewer carry forward as they continue watching? Carry wonder that is disciplined. Carry excitement that is patient. Carry the willingness to be surprised without being careless. The universe does not owe us a simple answer. It offers clues, and it asks whether we are mature enough to interpret them with both imagination and restraint. In the meditative spirit of this channel, I will end this segment with a soft but sharp invitation. If the data truly suggests a living process on a world far away, what does that do to your sense of self, to your faith, to your fear, to your hope? Are you moved by the idea that life might be inevitable wherever chemistry and time are given room to breathe? Or do you feel the cautious voice of Sagan insisting that we slow down and demand more evidence before we celebrate? Leave your view in the comments. Not just a yes or no, but the reason your mind chooses its stance. And now let us step into the heart of the investigation, because the next part matters most. Have we truly found signs of life beyond Earth? Or have we simply discovered how easily the cosmos can imitate the shape of life with nothing but physics and light? Why did K218b spend years wearing the wrong label? A world too big, too heavy, too wrapped in hydrogen to ever cradle anything alive. Because in science, first impressions often come from the kinds of worlds we already know. And for a long time, we treated Earth as the only believable template for life. A planet more massive than Earth feels intimidating in the human imagination, like a mountain you cannot climb because gravity itself pulls harder on every breath. Stronger gravity suggests higher pressure at the bird surface. thicker air pressing down like a deep ocean that you cannot swim out of. And when the atmosphere is rich in hydrogen, many researchers once pictured a place more like a swollen mini Neptune than a gentle shore. Hydrogen is light as an atom, but as a blanket, it can become immense, deep, and unfamiliar. The old intuition said, thick hydrogen means crushing pressure, strange chemistry, and a surface that might be hidden beneath endless haze. It is easy to see why the early story leaned toward skepticism, because we fear what we cannot picture. And hydrogen worlds were not easy to picture with the tools we had. So K218b was quietly filed away in the mind as a difficult place. Maybe not impossible, but not worth emotional investment. Yet the universe has a habit of unsettling our neat drawers. It does not ask our permission before it invents new kinds of habitability. What changed was not the planet, but our ability to listen to it properly. When James Webb looks at a distant world, it does not see oceans or forests. It reads the thin handwriting of light. Each time K218b crosses in front of its star, a small portion of starlight filters through the planet's atmosphere. That atmosphere acts like stained glass in a cathedral of physics, absorbing certain wavelengths, letting others pass. And in those missing wavelengths, Webb can recognize molecules the way you recognize a familiar face by silhouette. This is the quiet miracle that made the old assumptions tremble. We stopped guessing what the air should be, and started measuring what it is. The measurements that matter most in this story are not dramatic in appearance. They are subtle signatures, a few notches in a spectrum. But subtle does not mean small in meaning, because a single molecule can be a door handle on a locked room. Webb's readings pointed to water vapor, methane, and carbon dioxide. That trio alone already changes the emotional temperature of the conversation, because it hints at active chemistry rather than sterile simplicity. Water vapor suggests that water is part of the system, moving between phases, participating in cycles rather than being absent like a forgotten word. Methane and carbon dioxide together invite the idea of chemical tension, a kind of imbalance that on Earth often travels with life's restless metabolism. Think of a sealed room. If nothing lives inside, the air settles into a quiet equilibrium. But if something breathes, the room never truly rests. Oxygen falls. Carbon dioxide rises. Chemistry becomes a moving story. That is why these gases feel like plot rather than decoration. Then comes the molecule that makes people sit up straighter in the dark. Dimethyl sulfide. DMS. On Earth, DMS is tightly associated with biology, especially microbial life in oceans. So, the mention of DMS carries a particular kind of electricity, not the loud thunder of certainty, but the sharp scent of possibility. If you want an image that fits in the mind, imagine standing on a beach at night, eyes closed, and recognizing the sea by smell alone. You do not see the water, yet your body knows it is there. A biosignature can feel like that. A chemical perfume drifting out of a hidden ecosystem. Of course, a responsible mind holds two truths at once: wonder and caution. Because nature can sometimes imitate life's handwriting, and the universe is clever in ways that keep scientists humble. Carl Sagan offered a compass for moments like this. Extraordinary claims require extraordinary evidence, That sentence is not cold skepticism. It is love for accuracy, a refusal to let desire outrun reality. And yet Sagan also gave us the softer flame that keeps us searching. Somewhere, something incredible is waiting to be known. Those two lines together feel like inhaling and exhaling, discipline and longing. They match the mood of Webb's discovery perfectly, because we are balancing on the edge between a measured result and a life-changing interpretation. Another voice that belongs in this moment is Vera Rubin's enduring spirit of curiosity. Though not as a slogan, but as an attitude. Keep looking, because the universe rewards patience. In that same spirit, Stephen Hawking once reminded us that we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. That contrast is the heartbeat of this story. Small creatures, large questions, and light as our messenger. Now, let me make the old objection tangible with a simple example. The pressure cooker. A high-gravity planet can be imagined as a pressure cooker world, where the atmosphere presses down and the chemistry behaves differently than on Earth. In that mental model, life seems doomed because we picture fragile organisms crushed before they begin. But life on Earth has already taught us a quieter lesson. Pressure is not always an enemy. It can be a shelter that stabilizes molecules and protects liquid water from boiling away. Deep-sea microbes on Earth do not complain about pressure. They use it as a normal condition of being. So when we hear strong gravity, we should translate it not into impossibility, but into difference. Here is another example. The blanket. A hydrogen-rich atmosphere can sound hostile, yet hydrogen is also an excellent heat carrier in the physics sense, able to redistribute warmth and soften extremes. So the same hydrogen that once looked like a suffocating shroud can also be imagined as a thermal quilt, reducing the violent temperature swings that sterilize worlds. A third example. The fingerprint on glass. Transmission spectroscopy is like holding a glass up to the light and discovering fingerprints you did not know were there, invisible until the angle is right. Webb changed the angle, and suddenly the planet's atmosphere left readable marks. These examples matter because they show how scientific progress often works, not by changing the universe, but by changing the metaphors we are allowed to use responsibly. In the older era, K218b was judged mostly by category. Too big, too gassy, too unlike Earth. In the newer era, it is judged by measurement, by actual molecules in actual starlight. And that is why this story feels so emotionally potent. It is the moment a distant world stops being an idea and becomes a system with chemistry you can name. Now, the most important bridge between the old skepticism and the new excitement is this. Habitability is not a single door. It is a hallway with many rooms. Earth is one room, but not the whole house. K218b invites us to imagine other rooms. Ocean worlds beneath thick atmospheres. Twilight climates around red stars. Ecosystems that do not rely on the familiar oxygen story. If DMS is truly present in a robust way, it suggests that the hallway might be far longer than we dared to hope. And even if future work reframes the signal, the deeper lesson remains. We now possess instruments that can test the question of life rather than only dream about it. That is a profound shift. Almost like the first time a stethoscope let a doctor hear a heartbeat inside a body rather than guess at health from the face. My personal view is that the most beautiful part of this discovery is not the headline number. It is the restoration of humility. We were too quick to dismiss worlds that did not match our comfort, and the universe answered by presenting a world that might be alive precisely because it is different. There is a meditative lesson here for anyone living on Earth, including me. We often confuse unfamiliar with impossible, and we often confuse category with truth. But nature does not live inside our categories. It flows around them like water around stones. If you sit with this for a moment, it becomes more than astronomy. It becomes a way of moving through life. Do not dismiss what you do not yet understand. Measure it carefully. Listen longer. Let reality reveal its own shape. The trotting part of me imagines K2-18b not as a data point, but as a distant breath under a red star, a slow pulse hidden behind clouds that glow like thin silk in infrared light. The Tianding part of me remembers that Webb itself sits in cold darkness far from Earth, a quiet mirror listening without desire, only attention. That is the posture we need as storytellers and as viewers. Attention without forcing conclusion. Wonder without surrendering rigor. So when you hear that K2-18b was once considered too harsh, let that be a reminder. Harshness is often just a name we give to complexity before we learn its rhythm. And when you hear that Webb found water vapor, methane, carbon dioxide, and a hint of DMS, let that be the moment you feel the scale of our era. Not because we have reached another world, but because we have learned to read the faint ink of its atmosphere across interstellar night. If the universe is a library, Webb is the lantern that finally lets us see the titles on books we could never touch. And among those titles, K2-18b is glowing with a question mark that feels like destiny. So breathe with that question. Do not rush. Because the next part of the story is where science becomes most thrilling. We must ask not only what was detected, but how confidently it was detected, and what alternative explanations must be tested until only the strongest remains. That is where curiosity becomes discipline, and where the promise of this world either solidifies into history or transforms into a deeper understanding of chemistry itself. And that is exactly why the question we began with deserves to return now. Sharper, heavier, and more alive than ever. Have we truly found signs of life beyond Earth? Have you ever wondered what it would feel like if an alien ocean exhaled and we could smell it from across the stars? Not with our noses, but with a mirror of gold hanging in the cold dark far beyond the moon. That is the quiet shock inside this moment. James Webb did not take a postcard photo of a shoreline or a creature. It did something far stranger and far more powerful. It listened to light passing through air. When a planet slides in front of its star, a thin ring of starlight threads through the planet atmosphere before reaching the telescope. That light is not just brightness. It is a message with missing notes. Because molecules in that alien air steal very specific colors from the starlight. Those missing colors form a pattern, a fingerprint, a signature that can be read even when the world itself is only a dot. This is why the abnormal discovery in the atmosphere matters. Webb did not simply find one gas. It found a meaningful combination: water vapor, methane, carbon dioxide, and then the molecule that makes every scientist sit up straighter: dimethyl sulfide, DMS. In the human story of science, there are discoveries that arrive like thunder, and others that arrive like incense drifting under a closed door. DMS belongs to the second kind, subtle but unsettling, because on Earth it is tied so tightly to biology that it feels like a whisper with a pulse. It is the kind of thing oceans make through living work, the kind of thing you would not expect rocks and lightning to sing into existence in the same way. Here is the part that I think people often miss. Webb is not claiming a miracle. It is measuring chemistry. And chemistry is the most honest language the universe has. A planet can lie to your imagination, but it cannot easily lie to a spectrum. Think of it like this. Imagine walking into a dark room where you cannot see anything, but you catch the scent of smoke. You do not yet know whether the fire is a candle, a fireplace, or a disaster. But you know something is happening. Water vapor is like the dampness you feel on your skin. Methane is like a faint sweetness that should not linger without being renewed. Carbon dioxide is the heavy breath of a world that processes energy. And DMS, in the imagination of astrobiology, is like hearing a soft footstep in a hallway you believed was empty. Of course, a careful mind must slow down here. Carl Sagan gave us the sentence that protects wonder from turning into gullibility. Extraordinary claims require extraordinary evidence. That line is not a cold shower on excitement. It is a warm hand on the shoulder, telling us to keep walking carefully so we do not fall into our own hopes. So the real question is not whether the signal feels dramatic. It is whether the explanation must be dramatic. This is why the video focus on the method matters, because the method is the bridge between poetry and proof. The bridge is called transmission spectroscopy, but you do not need the technical name to feel its elegance. A star becomes a backlight. A planet becomes a stained glass window. And the atmosphere becomes the colored dye that selects which hues survive the journey to Webb. If you have ever held a prism to sunlight and watched white light break into a rainbow, you have touched the same principle. Except now the rainbow is carved by molecules that may have never seen our sun. Or imagine a singer behind a curtain. You cannot see the person, but you recognize the voice from the tones that leak through. Webb recognizes gases the way your ear recognizes a familiar melody, by the places where the sound is absorbed or amplified. This is also why the mix of gases matters more than any single one. Water vapor tells you there is a cycle possible. Perhaps clouds and rain. Perhaps a deep reservoir beneath haze. Methane tells you there is a reduced carbon source that should not last forever without replenishment. Carbon dioxide tells you the world has carbon in circulation and likely some form of greenhouse behavior. Together they form a tension, not a quiet equilibrium. And tension is what life tends to maintain. Life is a habit of keeping the world slightly off balance, like a dancer constantly shifting weight to remain upright. A dead planet drifts toward stillness. A living planet tends to churn. Now place DMS into that picture. In astrobiology, a biosignature gas is often described in plain terms that even a tired mind can remember. A gas made by life that can build up in an atmosphere to levels we can detect. That idea is not romantic. It is practical. Because we cannot scoop an alien ocean into a lab yet, we search for what life would leave behind in the air, the way detectives search for fingerprints on glass. DMS is compelling because on Earth it is strongly associated with biology, especially ocean life. So when the spectrum hints at it, the heart naturally races, and the mind naturally argues back. Could geology imitate this? Could photochemistry fake it? Could data processing mistake noise for meaning? This is the mature form of awe, not blind belief, but a disciplined wonder that tests itself. To make it easier to picture, imagine you are far outside a city at night, and you see a faint glow on the horizon. A glow can be many things: a town, a factory, a wildfire, or a sunrise still hidden. You do not declare the cause immediately. You take more measurements. You look for patterns. You check the wind direction. In the same way, scientists treat DMS as a glow on the horizon of biology. Intriguing, suggestive, but requiring follow-up from many angles. Another example. Think of a crowded room where you cannot see anyone, but you hear laughter. Laughter suggests people, but you still ask whether it is a recording, an echo, or a trick of acoustics. DMS suggests life, but science still asks whether the universe has another way to create the same note. And one more. Imagine tasting salt on the wind while standing on a cliff. You cannot see the sea, yet the air tells you it is there. Atmospheres are like that. They carry stories from places we cannot reach. That is what makes this discovery so emotionally sharp. It is intimate and distant at the same time. A molecule touches a mirror, and suddenly your mind is swimming in an ocean you will never visit. But here is my personal view. The deepest value of this moment is not the percentage that makes headlines. It is the new humility it can teach us. Because whether the final answer becomes yes or no, the process reveals something profound. The universe is readable. It writes with light. It signs with molecules. And it allows a small species on a small world to decode the handwriting. That is already astonishing. The meditation hidden inside this science is simple. You do not need to touch a thing to understand it deeply. You can sit still and listen carefully, and the truth can cross impossible distances to meet you. Webb is like a monk of metal and mirrors, staying in darkness to see what bright places cannot see. At the same time, I think we must protect our audience from a different kind of story. The story that turns careful evidence into guaranteed life. Because if we promise certainty too early, we train people to distrust science when science behaves exactly as it should, by revising itself with better data. The real thrill is not that one paper or one observation ends the question. The real thrill is that the question is now measurable. We are not staring into darkness and wishing anymore. We are reading an atmosphere like a living page. And that leads to the quiet lesson I want to carry forward. In science and in life, meaning is often hidden in the smallest absences. In what is missing. In what should not be there. In the faintest deviation from silence. A single molecule can make us rewrite our map of reality. So, when you watch this segment about Webb and the atmosphere, let it be both a fire and a breath. Let it ignite curiosity, and also slow you into patience. Let it remind you that the universe does not shout. It suggests. And our job is to become worthy listeners, to earn the right to interpret a whisper as responsibly as we would interpret a scream. If you take one lesson from this story, take this. Wonder without discipline becomes fantasy. Discipline without wonder becomes sterile. The James Webb moment is beautiful because it holds both. a poetic hint, and a scientific standard. Extraordinary claims require extraordinary evidence, and extraordinary evidence begins with ordinary photons measured with extraordinary care. What if the most shocking proof of life is not a photograph of a creature, not a radio greeting, but a faint chemical perfume hidden inside a thread of starlight that crossed the dark for more than a century to reach our mirrors today? That is why dimethyl sulfide matters so much, and why it makes the story of K218b feel less like science fiction and more like a quiet turning point in human history. On Earth, DMS is strongly associated with biology, especially with marine ecosystems, where microscopic life releases sulfur compounds that drift upward into the sky and become part of the planet's breath. It is one of those molecules that feels strangely intimate, because it is not just chemistry in a vacuum. It is chemistry that so often carries the fingerprint of metabolism and food webs and living cycles. When people say DMS is produced only by life on Earth, they are pointing to a powerful pattern in what we have actually measured here at home. And yet the honest scientific posture must include humility, because the universe is a better chemist than our assumptions and can surprise us with abiotic pathways under exotic conditions we have never fully tested in laboratories for long enough. So the meaning of DMS is not that it is a magical stamp that guarantees life, but that it is a rare kind of clue that demands we pay attention and ask harder questions rather than dismissing the possibility out of habit or fear of being wrong. This is where the deeper idea becomes beautiful, because the most convincing argument for life is almost never a single molecule, standing alone like a lone candle in a storm. The strongest argument is a choir of signals that harmonize, a pattern that keeps insisting on itself even when you try to explain it away with geology and chance. That is exactly why the video's second pillar is so important: the concept of chemical disequilibrium. A dead world tends to relax into silence, into a kind of chemical stillness where reactions run to completion and the atmosphere settles into a stable mix that does not need constant renewal. A living world is different, because life is not content with equilibrium. Life eats gradients and makes gradients and refuses to let the air become boring. Life is a restless composer that keeps rewriting the same symphony of gases, pushing the atmosphere away from the easiest resting state and holding it there with endless small acts of metabolism. Here a famous line becomes more than poetry. It becomes a compass for how to think about living planets. James Lovelock once described Earth as a system in which life and environment co-evolve like partners in a long dance. Whether or not every detail of that grand idea holds in every case, the core intuition is still useful. Life behaves like a planetary force, not just a passenger. And Carl Sagan gave us a phrase that feels almost made for moments like this: we are a way for the cosmos to know itself. If that is true, then a biosignature is not merely data. It is the cosmos leaving a faint note that can be heard by minds made of star stuff and curiosity. So, when we talk about K218b and the idea of a living balance, we are really talking about a very specific style of evidence. Not a single gas in isolation, but a dynamic mixture that should not peacefully coexist unless something keeps it out of its comfort zone. On Earth is less than $0.5. Dollar is greater than consider oxygen and methane. Two gases that would rather destroy each other chemically over time. If we stopped biology on Earth like turning off a light, our sky would not keep its familiar character for long. It would drift toward a new steady state. Yet our atmosphere stays in a strange suspended tension, replenished every day by photosynthesis and respiration and microbial chemistry. That tension is not an accident. It is the signature of a planet that is doing something. A planet that is not merely sitting there. A planet that is behaving. Now, imagine explaining this to someone without equations, without spectral lines. Think of a bathtub. If the faucet is off and the drain is open, the water level settles. That is equilibrium. A dead planet behaves like the faucet is off. It can have interesting chemistry at first, but it eventually settles. A living planet behaves like someone keeps adjusting the faucet and the drain in tiny ways all the time, maintaining a level that would not persist on its own. That constant adjustment is metabolism written large, not as a heartbeat you can hear, but as a balance you can measure, even across interstellar distances. If your instruments are sensitive enough and your interpretation is cautious enough. Or take a simpler example. Think of a room filled with scented air freshener. If no one is spraying it anymore, the scent fades, the molecules break down or drift away. That fading is the natural trend towards stillness. If the scent stays strong day after day, you infer something is actively replenishing it. In the language of planets, certain gases are like scents that should fade unless renewed. So the question becomes not only what the scent is, but whether the room behaves like someone is still there, still acting, still breathing, still changing things, and refusing to let the air rest. This is why DMS is emotionally powerful as well as scientifically provocative. What if the first real hint of life beyond Earth is not a face in a telescope image? Not a radio hello, but a faint chemical breath hiding inside a thin ribbon of starlight that traveled for more than a century before it touched a golden mirror and became data on a screen? That is why dimethyl sulfide matters so intensely, and why people react to the letters DMS with a mixture of awe and caution. On Earth, DMS is strongly tied to biology in the real world we can sample and test and smell in ocean air. It is associated with living ecosystems, especially with microscopic life in seas and soils that processes sulfur as part of metabolism and releases sulfur-bearing molecules into the atmosphere. So when a distant world shows a possible trace of DMS, it feels like the universe has left a fingerprint on the glass of our instrument, as if an unseen ocean sighed and the sigh hardened into chemistry for us to read. That is the emotional core of the story. But the scientific heart must beat with honesty. And honesty means saying something simple and strong at the same time. DMS is not a magic stamp that proves life all by itself. Yet it is one of the more compelling candidates for a biosignature, because on Earth it is so closely linked to living processes, and so uncommon as a dominant product of ordinary geology in the environments we know well. The right way to think is to treat it like a bright flare in fog. It does not guarantee a lighthouse, but it absolutely justifies turning the ship toward it and looking harder. So the real question is not only what DMS could mean, but how it fits into a broader pattern that makes life the best explanation rather than a romantic hope. That brings us to the deeper idea the video leans on: chemical disequilibrium. A dead world tends to settle, like a bowl of water that stops rippling once you stop stirring it. Given enough time and no ongoing source of disruption, chemical reactions run toward a quieter state where the atmosphere becomes stable and predictable. A living world is different because life is a machine that runs on imbalance. Life consumes gradients and produces gradients. Life keeps stirring the bowl, so the surface never goes completely still. If you could measure a living atmosphere from far away, you would expect to see combinations of gases that should not comfortably coexist for long unless something is continually making them and removing them in a cycling way. That cycling is what metabolism looks like when it scales up from a cell to a planet. So the phrase living balance is almost paradoxical. It is balance maintained by constant change, stability sustained by unending activity. quiet kept alive by motion. Here is a comparison that makes it vivid without equations. Imagine a room with a candle and a window open. If no one tends the candle, the flame dies, and the room air becomes ordinary again. That is equilibrium. Now imagine the flame never goes out day after day. You infer an ongoing source of fuel and oxygen flow and careful conditions, even if you never see the person maintaining it. A chemically active atmosphere is like that. Flame. Not proof of a caretaker on its own, but a strong hint of continuing processes that must be explained. A living planet is the room where something keeps the flame alive. A second comparison. Think of a bathtub where the drain is open. If the faucet is off, the water level falls and then settles at empty. If the water level stays steady at a particular height, you know there must be an ongoing input matching the loss. Atmospheric disequilibrium is that steady level. And biology is one plausible faucet, because it constantly injects and removes reactive gases as a consequence of living chemistry. The planet does not need to be trying to send a message. It simply lives, and the air betrays it. The atmosphere becomes a public diary written in molecules, and we read it by starlight. That is the wonder of modern astronomy. We can infer behavior without direct contact. We can sense life like you sense someone behind a curtain by hearing breathing rather than seeing a face. And that is exactly how this story wants you to feel the data. Now place DMS inside that logic. DMS matters most when it appears alongside a pattern of gases that looks like a system kept out of rest. If a planet shows water vapor and carbon compounds and a persistent imbalance in ratios that should otherwise relax, then a hint of DMS starts to feel less like a random spark and more like a coherent signal, not a single clue, but a chorus, not a lone footprint, but a trail leading somewhere. In that framing, DMS is not the verdict. It is the witness statement that gains credibility when other witnesses agree. And when the video says the atmosphere behaves like it is being constantly adjusted, that is the key idea. Life does not allow the air to relax into the simplest state. It keeps the sky busy, like a city that never sleeps, powered by countless small transactions of energy and matter, too small to see individually, but unmistakable in total. If your measurements are good and your interpretation is careful, this is why the story feels like a threshold moment. Because for the first time, we are not merely imagining aliens. We are learning to recognize the chemical posture of life as a type of physics that refuses to be quiet. And that can be detected across interstellar distance, through light alone. If that does not make you pause and breathe a little slower, it should, because it reframes what it means to look at the night sky. The stars stop being cold decorations. They become possible neighborhoods, and chemistry becomes a language we can read, like Braille pressed into photons by alien air, long before humans ever knew how to build a mirror in space. That sense of delayed intimacy is profoundly moving. We are always seeing the past, and yet the past can still tell a living truth, like receiving a letter that was written a century ago but still smells faintly of the writer. That smell is what DMS symbolizes in the narrative. A molecule as a scent of a world. A trace that suggests oceans and cycles, and maybe drifting microbial clouds. Even if we cannot see a single cell, even the possibility is enough to change the mood of our era, because it shifts the question from are we alone to how common is life, and what forms can it take. And it forces us to accept that habitability may not mean Earth-like at all. It may mean balance in a different costume, a different set of gases, a different kind of sunlight, a different kind of ocean. Yet still the same underlying logic of persistence and cycling, the same refusal to settle, the same quiet insistence of metabolism against the pull of equilibrium. That is the philosophical punch behind the chemistry. Life is not merely a thing. It is an ongoing process that holds the world away from rest. Like a dancer who keeps turning so the music does not end. That is why disequilibrium is such a powerful word in this story. It feels technical, but it points to something deeply human: the recognition of activity, the recognition of presence, the recognition of a living system, even when it is unseen. Like realizing a forest is alive because the air changes under the canopy, and the scent shifts, and the silence is never truly silent, only layered, only breathing, only waiting for you to notice. In that sense, the universe is not empty, it is subtle, and we are finally building senses subtle enough to perceive it. That is what a great telescope really is: a new organ of perception for our species, not merely a tool. And the poetry of it is unavoidable, because when you decode a molecule from a far world, you have performed an act of remote empathy. You have listened to another planet's breath without touching it, without contaminating it, without claiming it, only by receiving light. That restraint feels almost ethical, and it points toward a better future for exploration, one where knowledge leads and conquest follows never. If there is a lesson here for us on Earth, it is that life is inseparable from balance, and balance is inseparable from responsibility. A planet that stays livable is not a planet that dominates its own systems. It is a planet that learns limits and feedback and cooperation. So when we get excited about a possible living world far away, we should also feel a mirror turning toward us, because it is painful and instructive that we can read stability in another atmosphere. While we struggle to keep stability in our own, the cosmos may be showing us a standard of endurance, not as a moral sermon, but as a physical reality. Survival is equilibrium maintained by wise cycling, not by endless extraction. That is my personal takeaway. The search for biosignatures is also a lesson in humility. It says that life is not only precious because it is rare, life is precious because it is a delicate kind of organized rebellion against decay, and it can be lost even when it is common elsewhere. So our wonder must become stewardship, not just entertainment, and our curiosity must become discipline, not just hunger for headlines. Because if we ever confirm that DMS and disequilibrium truly mark living chemistry on K218b or any other world, then the universe becomes a shared neighborhood of life, and the first rule of a neighborhood is respect. Respect for what you do not own. Respect for what you might harm by accident. Respect for the thinness of habitability, even when it looks vast from far away. In other words, the discovery would not only answer a scientific question, it would expand our moral horizon. It would demand a new maturity from our species, a maturity worthy of the ability to read life through light. This is where I like to borrow a thought in the spirit of Richard Feynman, who reminded us that nature cannot be fooled, and that the joy of discovery comes from admitting what we do not know while refusing to stop looking. That is the right tone here. Excitement without arrogance, hope without pretending we have certainty where we do not, and patience to keep testing alternative explanations until the simplest remaining story is also the truest. So yes, DMS is thrilling, because it resembles a biological signature we recognize from home. And yes, disequilibrium is persuasive, because it resembles the behavior of a living atmosphere rather than a resting one. But the most persuasive thing of all is the method itself, the slow, honest narrowing of possibilities, the refusal to declare victory too early, the willingness to be surprised by strange chemistry and stranger life. That method is the true hero of the story, and it deserves to be celebrated like a form of quiet meditation. Observe, question, test, doubt, refine. Observe again. Science at its best is attention trained to the point of reverence, and what James Webb represents is attention reaching farther than ever before. If the universe has living worlds in it, then the act of noticing them is already a kind of connection. We are not touching them yet, but we are hearing them in the only medium that crosses the void unchanged enough to carry meaning: light. So when you hear the words dimethyl sulfide and chemical disequilibrium, do not hear only jargon, hear a possibility. hear a distant tide under a crimson sky, hear the idea that life may be less an exception and more a tendency of matter given time, and then let that wonder do something practical inside you. Let it make you kinder to your own world, more careful with the thin air that keeps us alive, more patient with complexity, more eager to learn rather than to win arguments. Because if life exists elsewhere, it does not make us small, it makes us related, and relationship is responsibility. In the end, the most haunting part is this: the gases of a planet can become a message, even when no one intends to speak. A living world cannot help but leave traces in its air, and those traces ride photons across space like incense on a wind. When we decode them, we are not just collecting facts, we are participating in a conversation older than our species. The conversation between energy and order, between star and ocean, between chemistry and breath. So keep your excitement, but keep your rigor too. Hold both like two hands in prayer. One hand wonder, one hand skepticism, and between them a small glowing idea that somewhere beyond our reach a world may be quietly alive. What if the most important clue for alien life is not what we see in a spectrum, but what we do not see at all? When people hear about K2 18b, they often focus on the dramatic words, oceans, biosignatures, almost certain. But there is a quieter detail that can carry enormous weight: the near absence of ammonia. It is the kind of absence that behaves like a footprint in fresh snow, not a creature in view. Yet the path is unmistakable. In planetary science, we learn to treat an atmosphere as a living ledger of chemistry, a place where molecules are constantly being written, erased, and rewritten by physics and by whatever processes are active below. If a world is quiet and sterile, many gases drift toward a kind of calm balance over time, building up when there is no strong sink to remove them. Ammonia is one of those telling actors because it can be made by chemistry and geology in some settings, and it can also be rapidly consumed or transformed when a reactive environment has an efficient pathway to do so. So when the story says that a lifeless planet might tend to accumulate ammonia, the deeper idea is not a simplistic rule. It is a direction of reasoning. In the long run, without an active cycle that destroys it or locks it away, some atmospheres would be expected to show more of it than we observe here. And that makes the emptiness interesting. To make that feeling concrete, imagine a small closed room with a faint smell that should steadily grow stronger if nothing scrubs it out of the air. Yet day after day the smell never accumulates. You do not need to see the filter to suspect there is a filter, working continuously, invisibly, faithfully. Or think of an aquarium on Earth, where ammonia appears as waste and decay products in water, and if nothing processes it, it rises and poisons the system. But a mature aquarium with the right microbial community never lets ammonia dominate, because microscopic life turns it into other nitrogen compounds as part of a cycle that keeps the whole system stable enough for larger life to persist. That is not a perfect analogy for an exoplanet atmosphere, but it helps the listener feel why scientists lean forward when a gas is missing. Because missing can mean managed. In the same way, a kitchen without smoke after cooking does not prove a magical absence of fire. It suggests a vent is doing its job. The atmosphere of a world can be vented and scrubbed by geology, by photochemistry driven by starlight, by oceans that dissolve and trap molecules, and possibly by life itself. The art is not to jump to the last explanation first, but to notice when the ledger seems actively edited rather than passively drifting. Now the other half of this story carries a gentler kind of wonder. The planet appears to sit in a temperature regime that can allow liquid water to persist around 49 degrees Celsius as described. That number can sound unsettling at first, because our minds associate habitability with a narrow human comfort zone, a mild afternoon on Earth. Yet nature does not share our preferences. On our own planet, life flourishes in hot springs far above what we would call pleasant, and it survives in deep ocean environments where sunlight never reaches, powered by chemistry and heat rather than bright skies. So when the video says stable warmth, the important word is stable. Stability is a kind of mercy in physics. A planet that swings violently between boiling and freezing is a place where water can be present one moment and gone the next, where chemistry is constantly interrupted, and where delicate pathways struggle to continue long enough to become biology. But a world with a thick hydrogen atmosphere can behave like a great thermal blanket, holding heat and spreading it around the globe. Here a simple household image helps. A thermos does not create heat. It keeps heat from escaping too quickly. A heavy blanket does not generate warmth. It slows the leak of warmth into the night. In the planetary sense, hydrogen is light and efficient at moving energy through an atmosphere, so it can smooth extremes and distribute warmth from the day side to the night side. If you have ever walked near the ocean at dusk, you have felt a miniature version of this principle. Water and air storing energy and releasing it slowly so that temperatures do not crash immediately when the sun is gone. A thick atmosphere can do something similar at global scale, turning a harsh orbit into a more even climate where water can remain liquid rather than constantly switching state. And water staying liquid is not just a comfort detail. It is a chemical stage. Many of the reactions associated with life as we know it are profoundly easier in a stable liquid medium, because molecules can meet and separate repeatedly, because gradients can persist, because cycles can establish rhythm rather than chaos. This is where the ammonia point and the temperature point begin to hold hands rather than stand apart. A stable, warm environment with persistent, liquid water can support large-scale cycling between ocean and air. And if cycling exists, then certain gases will not merely accumulate. They will be processed. On Earth, the nitrogen cycle is not a decorative detail. It is one of the great quiet engines that makes long-term habitability possible. And ammonia is a key piece of that engine, produced here and consumed there, never allowed to dominate for long when the system is alive and balanced. So when a distant world shows a pattern that resembles management rather than drift, it invites a careful kind of hope. Of course, every honest scientist also carries a disciplined caution. The universe can mimic life with clever chemistry, and unfamiliar environments can produce outcomes that surprise our Earth-trained intuitions. This is why the strongest voices in science often sound both bold and restrained at the same time. Carl Sagan gave a line that remains a compass for moments like this. Extraordinary claims require extraordinary evidence. That sentence is not a wet blanket on wonder. It is a way to protect wonder from collapsing under its own excitement. And yet there is also a second Sagan truth that fits this story like a key. Somewhere something incredible is waiting to be known. When we combine those two sentiments, we get the proper posture for K2. 18b. Excitement without surrendering rigor. Curiosity without abandoning humility. Stephen Hawking once reminded us that we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe, and that makes us something very— what would it mean if an ocean far beyond our reach is not just water, but a different kind of breathing world? When I picture K2, 18b, I do not start with numbers or charts. I start with a horizon that never belonged to us. A horizon made of warm haze and heavy sky, where light from a red star falls like embers through curtains of hydrogen. The idea of an ocean hundreds of kilometers deep is almost too large for the mind, because our own seas already feel endless. Yet here the sea may not end at a familiar surface. It may fade upward into mist, then into cloud, then into air so thick it behaves like a slow liquid. You can imagine the boundary between sea and sky not as a line, but as a long, soft gradient. That is the first haunting beauty of this world. Pressure that would crush our machines might be ordinary there. Enormous pressure does not always mean violence. Sometimes it means stability. In a deep ocean on Earth, pressure is a constant hand on the shoulder of chemistry. It keeps water liquid where it might otherwise boil. It slows some reactions and accelerates others. It can protect delicate structures by keeping conditions steady. Now scale that idea up to a sea hundreds of kilometers deep, and you have a laboratory that never sleeps. A place where molecules meet again and again across ages that feel like meditation. Slow repetition, long patience, endless time for small patterns to become habits, for habits to become cycles, for cycles to become something we would finally call life. The thought that water could be mixed with hydrogen changes the taste of the imagination. On Earth, water is our familiar home solvent, and hydrogen is mostly a gas that escapes upward and away. On K2, 18b, hydrogen may be the great blanket, the great carrier of heat, the great softening force that smooths extremes across the planet. A hydrogen-rich environment might make the ocean behave differently, more compressible, more willing to hold dissolved gases, more able to sustain strange gradients of energy that living chemistry could exploit. Here is where science becomes a kind of poetry, because even when we speak carefully, we still feel the wonder of unknown, rules playing out far away. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That line matters here not as decoration, but as discipline. It reminds us to hold awe and skepticism together, like two hands carrying the same fragile bowl. We are not claiming to see fish or forests on K2. 18b. We are trying to read the atmosphere like a breath on cold glass, and then asking what sort of ocean could sustain that breath for long enough to be noticed across the dark. So what might that ocean look like if you could drift above it? I imagine a surface that is not bright blue, because the light is not bright yellow. Under a red dwarf sun, the palette shifts toward copper and rose, toward violet shadows and dim gold highlights. Waves might move with a slower rhythm if the air is dense and the winds are different. Storms might be broad rather than sharp, like weather that prefers long exhalations over sudden shouts. If clouds are thick and high, the sea might rarely see direct starlight. Instead, it would live under a constant twilight glow. That kind of softness matters, because stable light and stable temperature can be a cradle for complex chemistry. Not because comfort creates life, but because stability gives life time to learn itself. To make this easier to picture, take 3 scenes we already know on Earth. First, the hydrothermal vents on the deep ocean floor. There, sunlight is absent, yet ecosystems thrive. The energy comes from chemistry, from gradients, from reactions that release usable power for microbes and the creatures that depend on them. That is a living proof that oxygen and sunlight are not the only gates to biology. Second, the briny pockets beneath Antarctic ice. Hidden water persists in darkness and cold, protected by pressure and salt, inhabited by microbes that live quietly on scarce energy. This shows that life can endure with minimal fuel and extreme constraints. Third, the thick atmospheres of planets and moons in our own neighborhood. Titan comes to mind, where methane plays a role similar to water in shaping weather and surface processes. Titan teaches a gentle lesson that a world can run on different fluids and still have cycles and seasons and chemistry that feels alive in its own way. If Earth can host life at vents without sunlight, under ice without warmth, and within strange chemical niches we once thought sterile, then K2 18b does not need to mimic our comfort to be biologically interesting. Now comes the question that stirs the audience most deeply. Does life there need oxygen? We tend to worship oxygen because it powers large animals here, and because it is tied to fire, speed, and the kind of metabolism that built our muscles and brains. But oxygen is not a universal requirement. Many microbes on Earth do not use it at all, and some are harmed by it. In the earliest chapters of Earth, life existed long before oxygen filled the sky. If that is true here, then it can be true elsewhere. Charles Darwin wrote, "From so simple a beginning endless forms most beautiful and most wonderful have been, and are being, evolved." That sentence holds open the door we often shut too quickly. Endless forms means biology can be inventive under constraints that feel alien to us, and still remain biology. So when the video asks about organisms that might breathe hydrogen or live on methane, it is not fantasy in the childish sense. It is an informed expansion of possibility. Hydrogen can be fuel in certain chemical pathways. Methane can be both food and waste, depending on the ecosystem. And the key idea is not the specific molecule, but the cycle. Life is not a substance. It is a pattern of organized change that keeps itself going. Imagine an ocean world where the upper atmosphere is a slow ocean of gas, and within it float microbial mats like airborne plankton. They rise and fall with currents, feeding on trace chemicals, perhaps using dim red light when available, perhaps relying on chemical gradients when light fades. On Earth we have an analogy in the ocean itself, where plankton drift and bloom and reshape the chemistry of the air above them. The sea breathes through them. If K2 18b has vast oceans, then life could be most abundant, not on a shoreline, but throughout the volume of water and air in motion. A biosphere without continents, a living world where the idea of land is irrelevant. Another scene, deeper down. If the ocean is hundreds of kilometers deep, then there may be layers where temperature and pressure create chemistry we cannot easily reproduce. In those layers, reactions could build complex organics in slow, steady steps. Not a single lightning strike creating life in a moment, but trillions of gentle chances over vast time. That is why people call it prebiotic chemistry, the long prelude where matter learns the grammar of living systems. The pressure being extreme yet stable matters because stability is the friend of accumulation, and accumulation is the friend of complexity. When I analyze this content as a science communicator, I notice the strongest promise is not that we have found aliens. The promise is that we may be approaching a new kind of evidence. Not images of creatures, but signatures of metabolism. The atmosphere becomes the diary of the ocean beneath it, and telescopes become readers of that diary. We should still be careful, because nature can surprise us with abiotic pathways we have not yet mapped. Yet the direction is profound. We are learning to treat a planet like an integrated system, a coupled dance of ocean and sky, chemistry and climate, energy and time. Neil deGrasse Tyson has said, "The universe is in us." In this story, that is not just a poetic line. It is almost literal. The same physics that makes hydrogen abundant, the same carbon chemistry that builds organic molecules, the same tendency of energy to flow from high to create low, while creating pockets of order on the way. All of that is shared across worlds. If life exists under hydrogen skies, it would still be our cousin in the deepest sense, because it would be made from the same cosmic ingredients and the same universal rules. Here is a simple comparison to help the listener feel it. Think of Earth as a bright kitchen with many tools. Oxygen is one of the sharpest knives. Now imagine K2. 18b is a quiet kitchen with different tools. Fewer sharp edges. More slow cooking. More fermentation. You can still create nourishment. You can still create complexity. It just happens with different timing and different flavors. And now the part where my personal view enters. I do not think the most important outcome is winning an argument about whether K2 18b is inhabited today. I think the most important outcome is that we are being trained to loosen our ego as a species. We have a habit of turning Earth into the blueprint for everything meaningful. And that habit is understandable, because we love what made us. But it can also blind us. This topic invites a gentler mindset, a readiness to accept that the universe may be hospitable in ways that do not resemble our home. That is a spiritual lesson hiding inside a scientific one. It teaches humility without despair, wonder without gullibility, curiosity without conquest. If life can thrive in a hydrogen-rich ocean world around a red dwarf, then life is not a rare jewel locked in one kind of box. It is more like a melody that can be played in many keys. That metaphor matters because it changes how we treat our own world. When you realize life may be common in the cosmos, you do not value Earth less. You value it more carefully. Because then Earth is not the only garden, but it is our garden. And stewardship becomes a cosmic responsibility rather than a local preference. There is also a quiet ethical thread here. If we confirm biosignatures beyond Earth, even microbial ones, the way we explore must mature. The universe would no longer be a blank map. It would be a living neighborhood. And in a living neighborhood, you do not barge into a house with muddy shoes. You learn to knock, to listen, to protect what you do not yet understand. So I return to the original images. A deep ocean, water mixed with hydrogen, pressure immense yet stable. Those phrases are not just facts. They are invitations to imagine prebiotic chemistry as a slow prayer of matter, repeated over and over until it becomes self-sustaining. If oxygen is absent, life may still build itself around other electron acceptors and donors, around methane cycles, around hydrogen gradients. Biology is a master of improvisation, and the universe is generous with time. As a closing thought that ties the science to the feeling, I want the listener to carry this lesson into the rest of the video. We are not chasing a headline. We are learning a new way to read the cosmos. Oceans we cannot touch may still leave fingerprints in the sky above them. Life we cannot see may still reveal itself through imbalance and renewal. And if that is true, then every quiet star you have ever looked at may be more than light. It may be a lighthouse over an unseen sea. So, breathe with me for a moment. Let the scales soften your mind rather than overwhelm it. If an alien ocean can be stable for eons, then patience is not weakness. It is power. If life can exist without oxygen, then our definitions are not cages. They are temporary maps. And if K2, 18b, is even close to what we suspect, then the most poetic truth is also the most scientific one. We are part of a universe that keeps trying to become alive. What if the best place for life is not under a bright sun at all, but under a small red ember that refuses to die? That single idea flips a century of intuition on its head. We grew up imagining that life needs a star like ours, golden and strong, with clear seasons and familiar days. Yet the universe may prefer a quieter kind of guardian, the red dwarf star. Small, dim, and once dismissed as unwelcoming, it turns out to be something like a monastery lamp in cosmic darkness, steady enough for patience to become power. Red dwarfs live unimaginably long lives. Not just billions of years, but trillions of years for many of them. If our sun is a brilliant candle that will someday burn down, a red dwarf is more like a coal that glows quietly for ages beyond human storytelling. And when you think about what evolution truly needs, that longevity begins to sound like the most generous gift physics can offer. Life is not only about the right ingredients. It is also about uninterrupted time. On Earth, biology had to survive ice ages, asteroid impacts, volcanism and sudden climate swings. Those shocks shaped us, but they also reset the board again, and again. Around a calm red dwarf, a biosphere may get something rarer than sunlight. It may get continuity. A long, warm sentence that does not keep breaking in the middle. There is a reason this matters so much for worlds like K2-18b. If the star is steady, the planet can build a stable climate machine around that steadiness. A thick atmosphere can distribute heat like a slow river circulating warmth across an entire globe. Oceans can remain liquid without constant crisis. Chemistry can keep rehearsing the same reactions until the right pattern finally learns to copy itself. In that sense, a red dwarf is not a weak star. It is a patient teacher. It does not shout energy into space. It hums it. This is where the old misunderstanding becomes almost poetic. People once feared red dwarfs because their habitable zones lie close in. Close in means short orbits, strong gravity effects, and often tidal locking. The phrase tidal locking sounds like a curse. One face turned forever toward day, the other forever toward night. The imagination immediately paints a planet, split like a broken coin, half scorched, half frozen. But nature rarely obeys our first dramatic sketch. If the atmosphere is thick enough, if winds and clouds and oceans can move energy efficiently, the planet becomes less like a split coin and more like a breathing body. Heat flows. Pressure circulates. Storms transport energy the way blood transports oxygen. The day side warms the air. The air travels. The night side releases that warmth slowly. And instead of a hard boundary between fire and ice, you can get gradients, twilight belts, habitable regions that wrap around the globe like a soft ring. A simple example helps the mind hold it. Imagine a campfire on one side of a room. If the room has no air movement, the near side gets hot. The far side stays cold. Now imagine the room filled with thick air and powerful fans that never stop. The heat spreads everywhere. The extremes soften. And suddenly the entire space becomes livable. A tidally locked planet with a dense atmosphere can behave more like that second room. The physics is not a miracle. It is transport. It is the quiet labor of molecules moving energy from where it is abundant to where it is scarce. And if you want a second picture, imagine wrapping a warm stone in a thick blanket. The blanket does not create heat. It preserves and redistributes it. A hydrogen-rich atmosphere can play a similar role on some worlds. It can keep night-side temperatures from collapsing into lethal cold, and keep day-side temperatures from running away into lethal heat. So the question becomes less about whether one side is permanently day and the other permanently night, and more about whether the planet has a way to share its warmth generously. Now let us take a slower breath and look at the third idea, the one that makes even confident headlines feel strangely tender. Why do we call the light from K2-18b a message from the past? Because the universe does not deliver news instantly. It delivers it at the speed of light. And 120 light-years means 120 years of travel time for every photon that reaches our telescopes. So when James Webb receives a chemical fingerprint from that distant atmosphere, we are not watching the planet as it is today. We are watching it as it was when that light began its journey. Around the year 1905 on Earth, while a young civilization was learning new ideas about space and time, while early airplanes were still a brave experiment, those photons were already leaving an alien sky and crossing the dark between stars. That is not just a scientific fact. It is a meditation on distance. Here is an example that makes it emotionally real. If you receive a letter that has been traveling for 120 years, you would hold it differently. You would feel the fragility of paper and the weight of time in the same hand. Astronomy is exactly that kind of letter reading. Every spectrum is a postcard from a world you cannot touch, stamped not with ink but with wavelengths. And the strange beauty is that the postcard can still be truthful even if it is old. Because if a planet maintained a certain atmospheric pattern for decades or centuries, that stability itself becomes evidence of a living or at least active system. In other words, the past can be a strong witness if it arrives with clear fingerprints. This is why scientists care so much about certain molecules and about chemical imbalance. Life is not only a thing that exists, it is a thing that keeps working. It pushes against equilibrium. On a dead world, chemistry tends to settle into calm balance and stay there. On a living world, biology constantly disrupts that balance by feeding, exhaling, recycling, and reshaping its environment. So when a telescope detects patterns that look like persistent imbalance, we do not call it proof of aliens with cities, but we do call it a reason to pay attention with humility and rigor. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That sentence carries extra power here. Because Webb does not bring us a photograph of creatures. It brings us the suggestion of metabolism written in light. It is incredible precisely because it is subtle. And it is waiting to be known precisely because we must test it again and again to protect ourselves from wishful thinking. Neil deGrasse Tyson has also said, "The universe is under no obligation to make sense to you." A red dwarf planet that might be habitable while being tidally locked fits that lesson perfectly. Nature does not design for our comfort. It simply explores what the laws allow. If thick atmospheres can make permanent day and permanent night compatible with life, then the universe will use that option without asking our permission. And there is a third quote that sits gently underneath all of this. Carl Sagan also said, "We are made of star stuff." That is not only poetry. It is continuity. The same cosmic chemistry that built our oceans and our breath may be building other oceans and other breaths elsewhere. So when we talk about a red dwarf world sending us its ancient light, we are not only talking about distance. We are talking about kinship across physics. Let me offer 3 more concrete images to anchor everything. First, think of evolution like writing a long book by hand. Earth had many fires that burned chapters and forced rewrites. A stable red dwarf system might give life a quiet library where the book can be written without interruption for unimaginably long stretches of time. Second, think of tidal locking like living near a coastline that never moves. The sun never rises and never sets in the same way, but weather can still circulate like tides, and the habitable zone can be a permanent twilight shore, where temperature stays kind enough for chemistry to keep dreaming. Third, think of starlight as a time machine made of photons. When Webb looks at K2-18b, it is like watching a film reel mailed from another star. You are seeing a scene recorded long ago. Yet the fact that the reel exists at all tells you something profound about the reality that produced it. My personal view is this. The most moving part of the story is not the number 99.7. The most moving part is that the universe can be read at all. That a mirror floating far from Earth can collect faint infrared light and turn it into meaning. That we can sit on our small world and infer oceans we will never sail, clouds we will never stand beneath, and maybe life we will never meet. There is a kind of disciplined tenderness in that method. We do not shout into the cosmos with certainty. We listen to it with patience. That feels almost meditative. Breath in. The universe offers a signal. Breath out. We check it against every alternative explanation we can imagine. And the lesson I take from red dwarfs is surprisingly human. We often confuse brightness with value. We assume the loudest star must be the best home. But life may prefer stability over spectacle. A quiet light that lasts may be more generous than a brilliant light that burns out sooner. That lesson echoes back into our own lives. Sustainable warmth matters. Rhythm matters. Long patience can outgrow short intensity. So when someone asks, why would a small dim star be a better cradle for life? I think of the difference between a storm and a steady wind. The storm is dramatic. The steady wind shapes coastlines over time. Red dwarfs may be the steady wind of the galaxy. And when we add tidal locking to the picture, we see yet another reminder that extremes can be softened by connection. A planet does not need identical days, everywhere. It needs circulation. It needs sharing. It needs the ability to move energy from abundance to need. That is a physical principle, and it is also an ethical metaphor if you let it be. Finally, the idea of receiving a message from 1905 reminds me to hold discovery with humility. We are always late to the truth of distant worlds. We are always listening to echoes. And yet echoes can still change everything. Because even an old signal can tell you that the universe is not empty of process, not empty of chemistry, and perhaps not empty of life. If that possibility is real, then the night sky is no longer a ceiling of cold lights. It is a field of slow-breathing systems, each with its own weather, its own time, its own chance to become alive. So I leave you with one quiet thought to carry into the next part of the story. A red dwarf does not blaze. It endures. A tidally locked world does not have to break into extremes. It can learn to circulate its warmth. And starlight does not only illuminate space. It carries time itself like a river carries memories. If you let that sink in for a moment, you can feel the universe become less like a cold map and more like a living poem written very slowly. What if the universe has been speaking all along, and only now we have built an ear quiet enough to hear it? This is what the K218b story feels like. Not a fantasy of finding a second Earth, but a serious challenge to the way we define a living world. For decades we trained our hope on a familiar silhouette, a rocky twin with blue skies and oceans like ours. Yet the video insists on a calmer and more unsettling truth. Life may not need our exact blueprint. It may need balance, workable chemistry, and the long patience of time. In that sense, the discovery is not just about a planet. It is about humility. It asks us to stop demanding that the cosmos look like home before we allow it to be alive. When James Webb reads an atmosphere, it is not taking a photograph. It is reading a poem written in light. The starlight passes through alien air. Molecules take their tiny bites out of specific wavelengths. And what arrives is a fingerprint of chemistry. The video frames this as a turning point because it shifts the argument from storytelling to measurement. Not long ago, the idea of life elsewhere lived mostly in philosophy and science fiction. Now the claim becomes narrower and stronger. Not that we have seen a fish leap from an alien ocean, but that the air itself behaves as if something is feeding, breathing, recycling. That is the deeper meaning of redefining habitability. A planet can be strange and still be stable, unfamiliar and still be fertile for biology. Think of it with a simple image: a candle flame in a windless room. If the air is perfectly still, the flame holds steady and the chemistry around it settles into predictability. But if a living creature is breathing nearby, the air is never fully still. It is constantly nudged, reshaped, kept away from perfect equilibrium. Life is a disturbance that refuses to end. The video leans on that idea, that certain combinations of gases are not just ingredients, they are behavior. On Earth, our atmosphere is not a quiet archive. It is an active conversation between ocean, rock, and biology. So when a distant atmosphere looks chemically restless in the right way, it becomes a hint that something is doing work there. This is why the phrase in the title feels so electric. 99.7% chance of life. Even if we treat the number with scientific caution, the emotional impact is obvious. It is a door cracking open. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That line matters here, because it captures the mood of this moment. A patient search suddenly rewarded by a signal that feels personal. Not personal because it is about us, but personal because it touches the oldest human loneliness. Are we a solitary flame in an endless dark, or one candle among countless unseen lights? From that point, the video widens the frame and lands on the red dwarf fact. If stars like our Sun are the elegant classics, red dwarfs are the quiet majority. The video states they make up roughly 3/4 of the stars in the Milky Way. Now follow the chain of thought. If a common type of star can host a stable ocean world with the right chemistry, then habitability becomes less like a rare lottery win and more like a repeating pattern in nature. It is the difference between finding a single oasis in a desert and realizing the desert is dotted with springs you never mapped. One confirmed biosignature on a red dwarf world would echo far beyond one system, because it would suggest the galaxy has had many chances to get life started. Here is an example that makes this easier to feel. Imagine walking into a vast library at night. For years you believed only one book contained writing, the one you grew up with. Then you learn how to switch on a faint ultraviolet lamp, and suddenly you see invisible ink across shelves you thought were blank. James Webb is that lamp. It does not need to open every book and read every page. It only needs to reveal that the ink exists elsewhere. That single revelation changes the entire meaning of the library. The video then reaches the philosophical nerve, the end of the silent universe idea. For a long time, silence was not just a lack of radio signals. It was a story we told ourselves about being alone at the center of meaning. A measured hint of biology erodes that story, not with drama, but with discipline. Neil deGrasse Tyson has said, "The universe is under no obligation to make sense to you." In this context, it reads like a warning and a comfort. A warning that life may not resemble our expectations, and a comfort that the cosmos can still surprise us without needing our permission. If we insist that life must look like Earth, we may miss the most common forms of it. If we accept that life is a strategy for maintaining cycles and using energy, we become ready to recognize it in stranger clothing. This is where the new scientific era arrives naturally in the story. The video suggests astronomy, chemistry, and biology are merging into a single practice of listening for life through atmospheres. That is more than a new label. It is a shift in mindset. Astronomy used to map where things are. Now it begins to ask what things are doing. A planet, is no longer just mass and orbit. It is climate, feedback, disequilibrium, and perhaps metabolism. If that sounds abstract, consider a medical analogy. An X-ray shows the bones of a body, but a heartbeat monitor reveals behavior. Spectroscopy is becoming a kind of heartbeat monitor for worlds. Now for the open questions the video leaves us with. And these are the ones that linger like stars after you turn off the screen. If life exists there, how many forms can it take? Microbes floating in thick skies like plankton in an invisible sea. Chemistry-based ecosystems in deep oceans where sunlight is a rumor. Slow evolution under a steady red sun where time is so generous that complexity can bloom without constant catastrophe. And if the galaxy holds many such cradles, then our own existence changes meaning. We are not an exception tucked into a cosmic corner. We are an instance of a broader rule. Carl Sagan also said, "We are a way for the cosmos to know itself." If life is widespread, then the cosmos may know itself in countless ways, through many chemistries, many oceans, many skies. My own view is quietly two-sided. I feel awe, because the possibility of abundant life makes the universe feel warmer, less like an empty cathedral and more like a living forest at night. But I also feel responsibility, because if life is common, then life is precious in a different way. Precious not because it is rare, but because it is part of a vast and fragile continuity that we can either honor or interrupt. The lesson I take is simple and demanding. Do not confuse silence with absence. Do not confuse unfamiliarity with impossibility. And do not forget that the first world we must keep habitable is the one beneath our feet. Because it would be a strange tragedy to detect the breath of life across the stars while failing to protect the breath we share at home. So the final question is no longer only are we alone, but what kind of universe produces life so readily? And what kind of humans will we become once we know it? If K218b is alive, then the night sky is not a wall of distance. It is a coastline of neighbors we have not met. And if the universe is not silent, then every time we look up, we are not just observing, we are listening.